Hello and welcome to Datacast Solutions, Statistics and Data Mining 101 using Knime. This chapter begins the topic of data mining, and we're going to start with an introduction. Alright, before we take a deep dive into the specific mechanics around all the different data mining techniques that Knime supports, we need to cover some broad topics. These are generally topics that apply to almost all of the data mining techniques, and rather than cover them in each chapter, I'm going to cover them up front. The knowledge discovery goals are defined by the intended use of the application that you're building. First and foremost is usually the verification of a hypothesis, but the other is more common one, at least for me in business, is discovery. It's the prediction of future values or a description of the patterns that we see in the data. And the fitted models play the role of inferred knowledge. So there's going to be two types of learning that we're going to cover: supervised learning and unsupervised. In a supervised model, we're trying to discover the relationship between the independent variables and the dependent or predictor variable. The relationship is referred to as a model, a predictive model, and so on. Examples of this would be classification models, regression models, sequence models, or dependency link models. And it's all accomplished through an analysis of historical data that we're going to call a training set. There's also unsupervised learning. This is the analysis of historical data without a specified dependent variable. In other words, usually we're just clustering data together to find groups that exist within our data. What was intimidating to me when I began working with data science and data models was the wide variety of choices that I had, and it was overwhelming, I have to admit, and it is to the experienced person as well. However, there are only a few fundamental techniques that you're going to need to master in order to be an accomplished data scientist. A predictive model serves to classify new data and predict future values based on the content of the new data. Building this kind of model generally involves analyzing historical data to detect and identify the patterns, and basically building a formula that we can use to predict future records. And we begin this by dividing the historical data into two different data sets. The first data set we need is called the learning data set or the training data set. In our predictive model, it's going to study the contents of the training data set, and it's going to look for patterns and build a formula from it. So in other words, the training data set is a historical file that has the actual answer. So for example, let's say we had sales data and we were looking at training data of our sales. We would have an indicator that says, did we win or lose that sale? Maybe we won a certain percentage and we lost a certain percentage. And it'll be on region and salesmen and all kinds of different pieces of information. And what the machine algorithm is going to do is it's going to study the historical data and say, based on that, I see patterns that say, under this formula, you can predict which is going to be a sales win versus a sales loss. Now, the second data set is called the testing or validation data set. Since it's still historical data, but we know the outcome of the actual variables again. So once we've built our predictive model, once we built the formula using the learning data set, we're going to take the testing data set and apply that formula. So we'll compare the predicted results against the actual results, and that's how we'll measure how successful the formula that was generated is. In other words, its accuracy. So we'll learn to score a predictive model. So this is a very important distinction. The training data set is used to discover relationships, while the test data set is used to discover noise. Noise would be referred to as attributes or features columns in your data set that don't contribute to the actual outcome. Since all models pretty much need a learning and a test data set, they need to be set up in advance of building your data model. Now, there are many tools available for working with data sets, but I've rarely had to leave Knime. Knime has a very substantial set of tools built in to manage the process of randomly dividing, subsetting, and partitioning working with data in different forms. And you've seen some of that in the dimensional reduction workflows. So the first node that we're going to take advantage of is the partitioning node. So after reading a sample set of data that's going to represent all of our historical data, we want to divide that up into the training data set and the testing data set. And the partitioning node is going to be really helpful for doing that. Now, the partitioning node performs the exact same task as the sampling node. It extracts a sample of the input data, but it also builds a second data set with the remaining rows, those that weren't selected for sampling, and makes that available at a second port. So in other words, I can take my original data set and break it up into two parts. Now, you can specify the sample size as either a percentage of the original data set or an absolute set of numbers. So I might say 100 rows, or in my case, I've said 70% here. And then the extraction method includes, if you want it to run really fast, you can just say take it from the top, like give me the first 10 rows. Or you can use linear sampling, where it's going to take at a regular interval, every 10th row, etc. Draw randomly is just as it applies. It will just draw records randomly throughout the file. And a stratified sampling, if you choose that option, it will de-highlight the drop-down that has the columns in it. And you can specify the column that we'll use to create a stratified sample based on the distribution of that column. So for example, if you chose the stratification column of gender, you might say I've got 40% male, 40% female, and 20% unknown. And then finally, you'll notice the seed value. It's meant if you need to make your model reproducible and execute it over and over again, you can define a seed which would feed the random draw sampling. So that, in other words, this would produce the exact same results every time you ran it if you used a seed. And as I mentioned in the last slide, row sampling. That node provides the ability just to extract a sample of the input data. The rows that aren't selected, nothing happens to them. So otherwise, all of the meanings are exactly the same. Now, in data mining, you're going to hear the term overfitting a lot. And this refers to fitting a statistical model with too many degrees of freedom. It makes you too optimistic about how well your model is performing. And it's generally recognized as a violation of Occam's razor. The most simple explanation is the right one. It exaggerates minor fluctuations in the data and makes the model basically conform to fit the noise inside the data set. So in other words, it's not finding patterns in your data, it's memorizing your data. And that's not a good thing. And a clear indication that that's occurring is when the training set performance continues to improve while the test set performance does not. That means you're not discovering new patterns, you're actually just memorizing the patterns in the data. So what's going to cause you to build a model with overfitting? If the model is too complex, that's always a good sign. If the training data is too noisy, meaning small changes in little columns cause output data to change. If the training data set is too small, that's going to cause overfitting. And a very rich hypothesis space, meaning you've given yourself a lot of room for fudge. Two more terms you're going to hear in the development of models are bias and variance. Bias is the average difference between our estimate and the true mean. And when we have a large bias, the model is too simple and it does not fit the data very well. Variance, on the other hand, is the squared deviation of the predictor around its mean. A large variance means that the model is too complex. Small changes to the data change the model a lot. Neither of these are going to be good conditions. Let's look at how this might appear graphically. In the first chart, we can see the values expressed over time. Now, when I have a large bias and a small variance, well, the line would represent the mean, and the data moves a large bias. It's moving very far away from the mean at times. But the variance, the complexity of the function, is a straight line. It's a very simple, clear forward function. Now, with a moderate bias and a moderate variance, the data is a little closer to hanging around the mean line, but that's a little more complex of a function to draw out that line. And then finally, with a very small bias and a large variance, when I look at that graphically, I can see the data points are all but on the mean line, but the complexity of that model was very difficult, so the formula for producing that function would be very difficult. Now, a classic look at overfitting, again, by combining those all together now. The ideal boundary between the red balls and the green balls would be the solid black line that's slightly curved. And the two data points, the two grid points that are on the other side of that, that's noise. That's by definition an outlier in essence. Now, if I'm going to have a high bias, I'm going to draw the mean line right, the straight line with the dashes a little farther apart. And if I replace that with a high variance and I allow to incorporate that noise into the other side to stay with the green balls together, I made my variance too high. Now, with every model we build, we're trying to get accuracy is the goal. We're trying to get to be able to measure a prediction accuracy. The easiest way, of course, would be to just wait and see whether it's right or not. The drawbacks, well, you often can't wait. The prediction method changes, and it only tells you accuracy after the past prediction, meaning the sales, have you won or lost the sale? We've already lost the sale. It's too late. The primary goal is not to provide good or bad predictions, but to provide repeatable predictions. That's the goal. This is another visual example of what I was mentioning about overfitting. Model complexity versus prediction error. Remember I said that as we looked at if the model gets more and more complex, it gets less and less errors. Look at the blue line. As the model is very simple, it makes more errors in the training sample. But as the model gets more and more complex, it gets to be expert. In other words, it's memorizing all the patterns, every pattern that's there, and assigning them values. So your training data set just keeps getting perfect. But the red line, your testing sample, that will go down with the blue line only up until a certain point. And then all of that additional complexity that you built into your model isn't translating into better results on your testing sample. That's the indication of overfitting, and that overfitting is going to be caused by either, again, a high bias or a high variance, one way or the other. The solution to overfitting includes something called cross-validation, bootstrap regularization, and other advanced techniques. And we will point out some of these throughout the class. So cross-validation is a good example. I can basically take less data is discarded from the estimation process, which is going to reduce the variability by not relying on a single split. So I can take my learning data set and break it up into multiple parts and allow each one of those to go through and build a model. This is obviously not the most efficient process to solve for overfitting. But how do we prevent overfitting? Well, increase the sample size. The more data you have, the more likely it's going to be correct. Where possible, impute missing values. Missing values can cause a lot of damage to your model. Use a simpler model with fewer predictors, basically, in other words, making it less complex. A rough guide I can give you is at least 10 or 15 observations per variable is going to be necessary for it to be useful in a model. And a simpler model with fewer predictors, Occam's razor, is always going to be best. So in the coming chapters, we're going to examine all of the various techniques for supervised data mining and learning. That's going to include decision trees, naive Bayes, k-nearest neighbor, support vector machines, SVMs, neural networks, AdaBoost. These are all techniques that Knime will support. And we're also going to look at some unsupervised data mining techniques. And primarily that's going to be around association rules, which you might refer to as market basket analysis, k-means clustering, EM clustering, which is expectation maximization, and a few others. All right, chapter summary. We have supervised and unsupervised learning. Supervised is where we're discovering the relationship between the independent variables and the single dependent variable. In unsupervised, it's when we're trying to do analysis of historical data without a dependent variable. So we're generally just trying to identify groups. We have a training data set, and that's used to build the rules, the formula for prediction. The testing data set is to measure the accuracy of the formula that we've generated. Overfitting refers to fitting a statistical model with too many degrees of freedom so that it exaggerates minor fluctuations in data, making your model appear that it's better than it is. In general, recognized as a violation of Occam's razor. And finally, bias and variance. Bias is the average distance between the mean of our estimate and the true mean. And variance is the squared deviation of the predictor around its mean. Variation is explained by the model. That completes this chapter of the class. Feel free to move on to the next chapter.